Hello, let's do video number 11 in radioactivity, some applications of what we've learnt in radioactivity. Carbon dating is probably a very common example used in radioactivity, and let's just quickly go through what it is. It's a dating technique that can be used to date things up to about 30,000 years old, and therefore it's used a lot in archaeology and things like that. How does it work? Well, up in the atmosphere there's an isotope of nitrogen which is called nitrogen-14, and it's sitting around in the upper atmosphere, and we also have the sun. Now the sun's always giving off large amounts of charged particles, simply because it's a great big reactor in the sky, and those charged particles can make their way to Earth, and they can get through the Earth's magnetic field and interact with it even so, and we would see that in auroras, especially in winter. You may be lucky enough in Tasmania to see the occasional aurora. And what happens is this cosmic radiation comes in. This blue dot represents a neutron. It goes into the nitrogen-14 because it has a lot of velocity. It comes out of the sun very fast. It kicks out a proton, and because we're undergone neutron capture, we now have carbon-14 in the upper atmosphere. Now, the atmosphere is of course swirling around and equilibrating with the rest of the atmosphere, so this carbon-14 mixes in with all the other isotopes of carbon, and so we have carbon-12 and carbon-13. So when we're breathing in and out and eating things, we're eating carbon, and that carbon is a mixture of carbon-12, carbon-13 and carbon-14, and that's a constant ratio of those because we're constantly exchanging with the atmosphere. Now what happens though is when you die, you stop exchanging with the atmosphere, or all living things stop exchanging with the atmosphere, so whatever carbon atoms you had in you are trapped and they can't be exchanged anymore. And therefore what happens with burial is down here the carbon-14 decays by emitting a beta particle into nitrogen-14. And to date a material, what you do is you work out how much carbon-14 is left. And the less carbon-14 there is relative to the stable isotopes carbon-12 and carbon-13, the older the sample is because it has decay. So we could look at the half-life. I think it's about 3,000 years, 3,000, 4,000 years half-life, and so it decays. And so as soon as something is dead, the carbon-14 starts decaying and the amount of it will decrease, and therefore you can date it. And that's how carbon-14 dating works. Smoke detectors are another use. Now we've been using a americium-241 source, an alpha emitter, in our little pracs that we do, and so you've seen that this is a partially dissembled smoke detector, and the americium would be there protected by various layers, and we can see how does it actually detect smoke. Well, pretty simply really. The alpha source, being an alpha emitter, is fairly ionizing, so they have a current going through a small gap, so they have a positive and negative electrode, and the air gets ionized by the alpha particles, so a current will flow through. To have a current flow through air, you've got to have ions available, and if there's no ions there's no current will flow. And that's what happens when smoke stops the ionization process, or another way of thinking about it is smoke is basically carbon soot, and that absorbs all those free electrons, and so the current between these two electrodes stop, and then all the circuitry in the smoke detector says, hello, something's happened, set off the alarm. And that's why smoke detectors go off when if they're not positioned correctly, and some people put them in hallways close to kitchens and things, or even in their kitchen, and they're going off all the time because it doesn't really take much particulate matter like soot or even oil. When you're cooking a lot, you can get a lot of that vaporization of oil, and that will cause this to stop conducting electricity, and it will go off. Now there is another type of smoke detector that doesn't have any radioactivity involved in it, and that uses light, and it's a similar principle. Light beam across to some light sensors, and smoke goes in, you get less light, it gets detected, and the alarm goes off. Now the way to tell what sort of fire detector or smoke detector you have is the radioactive ones always have to have a label on them telling you that they've got a radioactive source in them, and they won't last too long. Americium decays fairly quickly, so if your smoke detector is older than 5 years or so, it's about time to get a new one, really, because it would have decayed to such an extent that it may not be functioning as well as it could be. Right, so that's smoke detectors. Another way is to use radioactivity, and in this case it's using gamma radiation. And what they do is sometimes when they drill holes into rocks, they want to actually know about the formations of rocks, and one way is to drill a hole and pull out a core sample, and that just tells you what's in that core, but that's a very expensive process. Got to use a big drill bit to just get a small amount of core. Very, very expensive. So another way is just to drill a hole, and instead of pulling the core out, they send down a density logger that uses a gamma emitter, and this slides down the hole, it emits gamma bounces back to the detectors, and you get a indication of the density of the rocks, and a geophysicist can then interpret that into the layering and the structure, and whether or not you've got oil, gas, coal, you could be looking for water even, all sorts of different things. So that's another use for it. There's a lot of medicinal uses for it in medicine, and one way is as using a radio tracer, which is just another word for an isotope that gets injected into the body, and it emits gamma radiation, and you want gamma radiation so it actually gets out of the body, doesn't get absorbed by the body, which is different from when you get something like where you actually get an alpha or a beta emitted injected into you, and you want it to go to the cancer and kill the cancer cells. This is for imaging and to work out what's inside you and what's going on. And so radioactive isotopes injected into you, the gamma goes to certain parts of your body, and this is a gamma detector that then creates a three-dimensional picture of your body. Looks very much like a CAT scan, but it's a different process. And this is a gamma knife, and how it works is, let's say this person might have a tumor in their brain, and so if we did a cross section, there's the head and there's our brain, sort of like that, a bit wonky, and let's say the cancer's just right in here, there's a tumor or something. Now that can't be operated on. Often the risks of the surgery are too great, and therefore the only treatment they have is something like this, which is a very clever way of doing it. Let's get a different colour. Yep, that will do. And so you position the patient's head inside this little ring, and they've got to actually drill little holes in your head so that it's always positioned in the same place, because you might get more than one treatment. And what they can then do is they have this ring around the person. Alright, it's getting more complicated as I draw. And what they do is they can introduce gamma radiation through these very accurate little tubes. And so they put a radioactive source in there, and then that directs a beam of gamma radiation. So if they want to, let's change that colour again. If they want to kill this one here, let's not go to that, let's go yellow. They send a beam in, and it goes like this. Oops, I missed it. That's terrible. Let's make that tumour a little bit bigger, hey? I'm going to have trouble hitting it. Right. Sorry, patient, but I just made your tumour a bit bigger. And so that beam goes through. Now, it means that all the parts of the brain there are getting gamma radiation, which isn't necessarily good for you. However, this beam is not very strong, and it's only on for a short period of time. So it's not enough to kill the brain cells. And so, but how does that kill the tumour? Well, they send in another beam in this way, and the beams are designed to intersect where the tumour is. And by the time you've sent a lot of beams through, okay, you can see that there's a focal point happening, and that's where the tumour is. And the rest of the brain is only getting a small amount of gamma in terms of the individual cells. And so that's a gamma knife. Very effective tool, regularly used in treating tumours and things. Right. Sorry, patient, for making your tumour bigger. Now, another use is to find out where cancers are. So in this case, someone swallows some radioactive iodine. It goes through your system, and the iodine collects in the thyroid system, and so they can then use a gamma probe to look at the thyroid system. This person here, this is a scan. There's their head, their arms are sticking up, and there's their trunk. And the bright spots are where the radioactive isotopes have gone. And so in this case, the radioactive isotope might be actually bonded to a chemical that goes to either cancerous cells, or particular types of cells, or particular types of chemicals. It's a very sophisticated chemistry going on, but it then gets concentrated, and so you can see there's not much radioactivity elsewhere, because all the isotope has gone to particular areas. So here they're looking at bones and bone structures or something like that. Okay, and they can use it in the brain as well. So lots and lots of uses of isotopes and radioactivity in medicine. Now, there's industrial uses as well. In most steel mills, anywhere that's using or want to be milling very hot steel, it's very hard to actually go and measure it because it's radiating a lot of heat, and they want to mill it to a certain thickness. And so what they do is they have big industrial rollers. This is white hot, comes out of the furnace white hot, and they roll it down to a certain thickness. And the way they can detect what thickness it is by using radioactive source and then a detector. And they could, well, here's a question: what sort of radioactivity would they use if they want to measure a sheet of steel that's so thick, a couple of centimeters thick? Well, clearly it would have to be something like a gamma emitter in that case, or they get really clever and they use a combination. They have a gamma emitter and, say, a beta emitter, and the beta emitter, if it's strong enough, they'll get some counts through it, but the gamma emitter, some of it will be absorbed, and so they can use the rate of absorption to tell the thickness of the steel, and it's all calibrated, and it's very accurate technique, and so they can move these rollers up and down to get it thicker or thinner depending on what they have to do. And that's used in just about every steel mill in the world. They also use radioactivity to look at steel beams, H-beams, where they have a sort of H shape. You see them on bridges, and actually Newstead College is made of a whole lot of them. And when they are squeezed, when the hot metal is squeezed through the H shape to get the H-beam, and it cools, there's no way of making sure that it's actually, or no easy way of making sure that there's no faults in the actual metal. But there is if you use radioactivity. And one of the most common faults is where there's bubbles, or there might be a thinness happening, which isn't apparent, but generally bubbling. And so here they have a radioactive source and your detector, and the beam absorbs all the radiation, and so that's a solid beam. This one's got air bubbles in it, so you get more going through, and therefore the detector detects it, and it can be rejected and remelted and made into another beam. Again, what sort of radiation would you use? Definitely not alpha, and probably gamma, with maybe a little bit of beta, if it's a strong beta emitter, but predominantly gamma emitter. Now there'll be a video on your OneNote about medical uses. I think this will be a link. I'll put a link to a click-through video that you can watch about some of the medical uses of isotopes. And in the next video, we're going to look at things called transmutations and chain reactions. Cheerio!